We are going to review question 2 next. If you have scanned through the whole question, you will notice that the bulk of the question is focusing on structural elucidation via NMR and IR spectra, as well as a little bit of mechanism related questions. Okay, so right now you are given this particular piece of information. The 1H NMR signals of protons on carbon atoms adjacent to CC double bond can be split by protons at the far end of CC double bond. If you scrutinize the structure, you notice that this particular CC double bond, or in fact all CC double bond, there's restricted bond rotation about it. That actually means that this particular group, okay, I'm going to highlight it in purple as HA, right? So the group containing HA is having a cis relationship with HC, okay, and the group containing HB, okay, over here, maybe I'll use another color, HB over here, right, is having a trans relationship with HC. Yeah, so that means that in any case, HA and HB, they are non-equivalent. Yeah, so being non-equivalent means that they could also potentially split each other. Okay, but of course, for this particular question, what was written here is a very simple fact. For example, it's mentioned that HA and HC will split each other with a small coupling constant. Coupling constant is not in the H3 curriculum, but it doesn't really matter over here. Yeah, because they are just telling you a fact. Yeah, basically it's measured in hertz. Yeah, so the greater the influence of the protons have on each other, the larger will be the coupling constant. Yeah, so they are saying that because A and C split each other, they have a small coupling constant. So B and C also split each other, and in most cases, AC and BC are not equal, for a very simple reason, because HA and HB are in different chemical environments. Yeah, but the value will be quite similar, but they are not the same. Okay, and it's also mentioned here that protons HA and HB are not equivalent because of the restricted bond rotation. Okay, so for parts A, you were told that propanone undergoes the following sequence of reaction. You are probably not familiar with barium hydroxide being used as a reactant. Okay, but in most synthetic process, barium hydroxide is kind of preferred for reasons we will not discuss over here. Yeah, so it's actually being used as a base to abstract the alpha protons, and in the process allows aldol reaction to take place. And then of course, the presence of corn phosphoric acid is likely to be some form of a dehydration reaction. Yeah, but again, you are not supposed to know this reaction by any means for H3. Yeah, so do not second guess what is likely to take place, although you can have some idea, but the best way to go about doing this question is really to work through the spectra. Okay, so you were told that the infrared and 1H NMR spectra of compound C are shown in figure 2.1 and figure 2.2. So if you take a look at figure 2.1, what is very obvious is over here, the very strong and broad OH stretch, and this is typical in alcohols. Yeah, so if you are looking at this portion, it is actually quite common, the sp3ch stretch. Yeah, so if you want to mention it, you can mention it, but other than that, it shouldn't be part of your answer. I mean, if you can mention it, but it's not like supremely important, because at the end of the day, for IR spectrum, we want to fish out the most important functional group for discussion. Okay, and of course, this is not to be missed. Okay, so this is the C double bond O stretch in ketone, and it's a very strong one. Okay, so take note of that. Okay, and of course, in the presentation of your answer, you should be tabulating your answers, right? So you should discuss the appearance, you should write down your deduction, and then of course indicate the region of the wave numbers you are dealing with. So over here, because I'm discussing the thought process in doing it, I'm not going to do the tabulation for you. Okay, and then moving on to the 1H NMR, you notice that there is a total of 12 protons, 12 H's. Okay, so if you take a look at the original propanone, right, there are 6 H in total. Yeah, so you could guess that probably C is formed from some form of reaction between two propanone molecules. Okay, right? Yeah. So of course, the most obvious example will be this particular signal over here, which contains 6 hydrogen. So this is a singlet. Okay, so a singlet containing 6 hydrogen. So it is likely to tell you that these are 2 methyl groups with no neighboring protons. Yeah, because it's a very clear singlet. And of course, the next signal that caught my eyes is this one, H. We call this Broad's singlet. Okay, because you will notice the base is quite broad. This is usually due to the Labile protons in OH. Yeah, so you can indicate this Labile protons in alcohol, or you can just say 1H. And this actually corresponds to the Broad's OH stretch observed in the IR spectrum. Okay, so I think you should be using both spectra to confirm with the clues that you get from each spectra should help you confirm the likely functional group or the likely connectivity in the final molecule. Okay, so that's what you should do. And then of course you are left with a 2H and a 3H here, which could pose some problems. Yeah, but not to worry, because you notice that they are all singlets. So being all singlet actually give us a very important clue. So that means that they are not bonded to a carbon that contains H, or they are not bonded to groups containing non-labile protons. Yeah, so that is a very important clue, which I think you need to take note of. And of course, in most cases, the easiest way to perform a deduction is really to look at this 3 H's over here. Yeah, because normally if you have 3 H's singlet, that means that it is a methyl group. And having a chemical shift of about 2.2 parts per million, okay, so that actually tells you that it is bonded to a highly withdrawing group, or a strong electron withdrawing functional group. And this is actually characteristic of propanone. Yeah, so that means that one of the CH3 here is likely to be present. And then of course, for propanone you expect 6 hydrogen in that region. Okay, but here I only have 3. So that means that one of the CH3 remains. Okay, so I'll just write one of the CH3 remains with a double bond O. Yeah, so that's my postulate. And then of course, moving on, you notice that there are 2 H's here. So that means that it is likely that there's a group containing a CH2. Okay, and you notice that the 2H, this particular signal and this particular signal, they are quite near each other. So that means that they are likely to be bonded to the same electron withdrawing group. But of course, the 2H is a little bit more disjunted. So that means that nearby there is likely to be another strongly electron withdrawing group. Or well, I mean, in this case, based on the clue given to you, it could be an OH. Yeah, so with all this coming into the picture, I'm just going to complete the diagram, because I've already accounted for the CH3, which is this, as well as the CH2, which is this. Okay, I'm left with 6H and then 1H. So I must be able to draw out a structure where it has 2 equivalent CH3. So it must be single bond throughout. So with that, it is likely that this is a CH3. This is a CH3. Okay, and then in order for the 2CH3 over here to have a chemical shift that is slightly above 1, because normally CH3 right at the end, right, they have a chemical shift below 1. If they are slightly above 1, that means that it must be influenced by an electronegative atom, or maybe a group that is slightly withdrawing, or maybe withdrawing via the sigma bonding framework, in that sense. Okay, so in this case, I'm left with OH, because this is the labile proton that we need to account for over by the Broad's singlet. Okay, so with that, this is likely to be the structure of compound C. Of course, we cannot make any confirmation of our answer without looking at one final data, that is the mass spec. Okay, so for here, the mass spec, we were told that it has a small molecular ion peak at 116. Okay, so if we take a look at propanone, this is actually 15 plus 15 plus 28. Okay, so in total this will be 58. Okay, so essentially you are expecting C to be something like a dimer, but in this case obviously it's not a dimer. Yeah, so it's a combination of two propanone molecules. So because this is, if you multiply this by 2, you are going to get 116. Okay, and of course you were told that it has some of these major peaks. Okay, how do we account for these major peaks? I think we can do that quite easily. Okay, so first of all, right, I'm just going to use maybe a pink color. Okay, so if we are going to cut off this portion during the fragmentation, the CH3 plus is likely to be seen in the MZ value of 15. Okay, what about 43? Okay, so 43 is likely to be over this. So remember that this molecule, or rather this fragment, is extremely stable. Okay, a CH3CO plus. Yeah, so it's likely to be this fragment as well. You don't have to draw it this way. You can actually draw it like this in normal circumstances. Yeah, but of course the more stable resonance stabilized form is the one with the triple bond O plus. Okay, and then of course next we look at 58. Yeah, so again 58, it is likely to be some form of a Lafferty kind of rearrangement, and then of course eventually we're going to end up with propanone with a plus charge. Okay, and of course for 101 essentially is 116 minus 101, so 15, the methyl group is gone. So based on this, I'm expecting this fragment to be cut off over here, so this whole portion is 101. Okay, so with that, it seems to correlate with what we have postulated. So the structure of C is likely to be the one I've drawn. Okay, so next we're going to move on to part 2. The next part, okay, it's a long part as well. So we have the infrared and 1H NMR of compound D, shown in figure 2.3 and 2.4. Okay, so if we go back to the question, D is produced when C is subjected to corn phosphoric acid and warm. Yeah, as I mentioned earlier on, this is likely to be some form of a dehydration. So again, we need to confirm by looking at the 1H NMR and mass spec, and IR. Okay, so immediately you notice that the OH stretch is gone, and then of course you are left with some of the sp3ch stretch, and then of course and a little bit of sp2 ch stretch over here. Maybe it's more of this portion. Okay, just slightly above 3000. Okay, then after that you notice that these two lines are now very sharp. Okay, what are they the same? Nope. Okay, so if you look at 1700, it's likely to be a C double bond O stretch, and then of course if you look at 1600, it's likely to be a C double bond C stretch. Okay, so these are all strong and sharp, and then these have to be included in your answer. Okay, then if you look at the 1H NMR, of course things will become a little bit more obvious. Okay, why does it become a little bit more obvious? Okay, so because number one, you have this proton signal at about 6 ppm, and this is characteristic of a hydrogen bonded to a sp2 hybridized carbon that is part of a CC double bond system. Yeah, so we call that a phenolic proton. Yeah, so over here you can conclude that there is one phenolic protons, and then of course we have expansion of the spectrum from 1.8 to 2.2 ppm, and then you notice that the CH3 signal, okay, because 3H is likely due to a CH3 signal, okay, is splitted into a doublet, so they are likely to be splitted by the 1H that is over here, that is what we call the phenolic protons earlier on. Yeah, because the 2-methyl group is likely to be non-equivalent, and that's why we have such a signal. And then of course, right now we have a singlet, the 1H, and this 3 hydrogen with that singlet. Okay, so that is very close to 2.2 and almost merging with the doublet over there. Okay, so in that case, this is likely to be the original CH3 that is bonded to the C double bond O. Yeah, so remember earlier on, right, the structure of C looks like this. Okay, yeah, so over here, we are trying to say that this actually gets sort of retained over here. Okay, and then perhaps this becomes the phenolic proton. Yeah, and then of course the OH is gone. So with that coming into the picture, what we can do is we can erase this portion. So if we can confidently say that some form of dehydration have taken place, this double bond is being produced over here, and this H, okay, this is the phenolic protons, and of course we have 3 non-equivalent or rather 2 non-equivalent CH3, okay, and these 2 are being splitted by the phenolic proton into a doublet each, and they are non-equivalent because of the restricted bond rotation about the CC double bond. Okay, so with that, I think we can confidently say that D is likely to have this particular structure. Yeah, and then of course, those of you who are familiar with this is actually what we call the aldol condensation product. And this is what we call an alpha beta unsaturated carbonyl. Yeah, and then you might be wondering why is this produced instead of, say, something like this. The reason is because the double bond that is formed is conjugated with the C double bond O. Yeah, so because of that, the alpha beta, this alpha beta unsaturated carbonyl is preferred over the beta gamma unsaturated carbonyls. Okay, so with that, for part 2, we have successfully explained how we deduce the structure of D. Okay, and then for part 3, we are supposed to suggest a mechanism for the reaction of C with warm corn phosphoric acid to produce D. And then we are supposed to label the rate determining step. Okay, so this mechanism shouldn't be too difficult, because what we have here is something like this, and then we have OH. Okay, so you might be thinking, what is the role of phosphoric acid? Of course, it is to protonate the alcohol group. Yeah, these are the usual things you have learned. Remember that in an acidic medium, OH cannot live as OH minus because it's a very, very poor living group, and that usually involve a very, very high activation barrier. So with that, I'm going to just draw out phosphoric acid. Many a times student asks, is it necessary to draw out phosphoric acid, or can we just put it as H+? My suggestion is, since the question gave your phosphoric acid, then you just draw it out. Okay, so this result in the protonation, okay, of the OH group. So in order to keep myself consistent with H2, I'll just put delta plus, delta minus. Okay, and then of course the OH bond will break heterolytically, and then the O will gain a -1 charge. Yeah, this is one way you can draw the mechanism. Yeah, but if you follow what we talk about to draw mechanism from the electron source, the electron sink, you can actually push your arrow towards the withdrawing P11O. Yeah, the outcome is the same. Okay, yeah. So after that, I'm going to draw out the intermediate, which is actually a good leaving group. Okay, so this takes on a plus charge. Okay, and of course the rate determining step involve the heterolytic cleavage of the CO bond. So this is the RDS. Okay, and then of course this breaks. Okay, and then of course I have H2O being produced, and then at the same time I'm going to form a carbocation, and then of course the H will be lost as a H+. Okay, if you wish to, you can use the conjugate acids, the conjugate base, to abstract this particular proton. So I can just put a P double bond O H O O H O minus. Okay, I can just let it grab the H here, and then of course eventually I'm just going to get the alpha beta unsaturated carbonyl plus H3PO4. Yep, so that's how I will illustrate the mechanism leading to D from C using concentrated phosphoric acid as dehydrating agent. Okay, and then for part 4, we were told that the reaction of C with corn phosphoric acid could produce 2 possible constitutional isomers. So we were asked to draw the other constitutional isomers and explain why D is formed rather than the other isomers. I think I've drawn it here. Yeah, so it has been addressed earlier on. So this is actually not preferred, but the alpha beta unsaturated carbonyl, that is D, is preferred. Why is that the case? Because the CC pi system is conjugated with the CO pi system. Yeah, this particular conjugation will help to stabilize it more than the non-conjugated version. Okay, yep. With that, we're going to move on to the next part, which is part B. For part B, we were told that another sequence of reactions starting with propanone is shown in figure 2.5. So again, we have corn sulfuric acid. Okay, and then we get E. You notice that this is actually some form of aldol condensation as well. Okay, I will not go into the mechanism, but if you are interested, you can try to draw the mechanism. Okay, and then we have ammonia being introduced and we get F. Yeah, so again from E to F, this is not a reaction which you have learned in H3. Yeah, so I need to emphasize, or rather we need to emphasize, that there isn't a need for you to go and learn new reactions, because whatever you need to do in this question is to look through the spectra given and then deduce the answer on your own. Okay, but for those of you interested, this reaction is actually known as conjugate addition, or some form, I mean it's a series of conjugate addition, it's not just one off. Okay, so ammonia is a base, okay, with a lone pair on the end. So if you look at this particular structure, delta minus over at the carbonyl oxygen, delta plus at the carbonyl carbon, and then we have delta minus, delta plus. Okay, so a conjugate kind of reaction can take place. Okay, and then it goes through a series of mechanism, and then you have to just draw the arrows, or sketch through the mechanism if you wish to get compound F. Okay, if not, then it is fine. You can just solve for compound F quite easily. Right? Okay, so right now we are given figure 2.1, table 2.1 I mean, and then we have the 1H NMR of compound F. Okay, so we notice that there are 12 hydrogen, singlet 1.04. Yeah, so if I try to correlate this, can you see that these 4 CH3 kind of remain intact in the product F, likely to be. Yeah, so that means that they are quite isolated, meaning that it is likely that they are bonded to a carbon with no proton to split them up, because now we have a singlet at 1.04, and 1.04 is very near to 1. That means that you are expecting it to be below 1, because remember, CH3 right at the end, normally for a straight chain structure it should be below 1, but right now it's not below 1, it's like 1.04, close to below 1 but not quite there. So that means that they are likely to be bonded to maybe some groups through a sigma bond that is perhaps electron withdrawing, or maybe a bit more electronegative than carbon. Yeah. Okay, and then the next clue we can look at is 2.33, which is a singlet, and then over here 4 protons. Yeah, 4 protons is usually quite tough, because you can't have like a carbon bonded to 4 hydrogen besides methane. Yeah, so therefore if I'm given that it's a singlet, okay, so this is likely to be a CH2. Okay, but of course a CH2 next to groups that are not able to split the protons. Yeah, so with that, can you sort of see the picture? maybe I'm just going to highlight that these two carbon I've highlighted in purple, right? They are likely to become CH2. Okay, and that makes sense because if they are CH2, then they are next to the carbonyl carbon, and that explains why the chemical shift is quite high, like 2.33. Okay, so right now everything makes sense. And finally, we have this broad singlets with only one proton. So the broad singlet is a telltale sign, one proton. So that means that this structure is likely to be an amine, and in particular, a secondary amine. Okay, why secondary amine? Primary amine has 2 H, tertiary amine no H. Yeah, so only secondary amine. And then that kind of makes sense. So using the structure of E, it is likely that the structure of F will be quite similar. So this thing will be kept with an NH here. Okay, so remember that these two ends are kept. Okay, yeah, so if I number the carbon, that's 1, 2, 3, 4. Okay, so I'm going to do the same thing. This is 1. Sorry, this is 1, 2, and then 3, 4. Of course, the carbonyl carbon I can number it as 5, so this is 5. Okay, and then of course the N here, as what I mentioned to you all earlier on, it undergoes some form of a conjugate addition, maybe 2 times in order to get compound F. Okay, yeah, and then of course we just focus on the 1H NMR, and it's true enough, in most cases focusing on 1H NMR can give us the answer, but we need to verify it by looking at the IR data. So the IR data tells us that there's a strong peak at 1700, so that tells us that the C double bond O stretch is still present, so the ketone group remains, and a weak peak at the 3320. So that means that we are looking at a NH stretch due to a secondary amine. Okay, yeah. And then of course, I think the only other things I have not sort of mentioned is that why is it that the CH3 over here, their chemical shift is not below 1? Yeah, so remember earlier on we are saying that the quaternary carbon bonded to these CH3, right, they are likely to be bonded to an atom that is more electronegative than carbon, and true enough, in this case, is nitrogen. Yeah, so the slightly, the more electronegative nitrogen has some impact on the CH3, but not a direct full impact, and that's why their chemical shift is still well below 2, but not below 1. Okay, so with that, that will be the end of the review to question 2.